Good morning for you in Brazil and good afternoon for me here in Finland. I want to thank you very much, the organizers, for the opportunity to give this little 3 lectures course. And what we are going to talk about today is sustainability, but I want us to think about sustainability from a technical, an economic, and an environmental perspective. And I will try the best that I can to present examples or apply in a very simple way, in a very basic way, sustainability to nano and nano products of bioproducts or projects or technology, so that we can see what we're talking about into a practical way. So my name is Luana Dessbesell. I am Brazilian and Canadian, and I'm a professor, an assistant professor at Aalto University in Finland as part of the School of Chemical Engineering and as part of the department called Bioproducts and Biosystems. And I'm also part of the Bioinnovation Center, which is a new center of excellence here at Aalto that focus at the moment in textiles and packaging for bio-based resources. So that's a little bit about myself. And today for the course, I hope that in this first lecture, I think we have about 45 minutes, 50 minutes, and then there will be questions when we come live during the event. So during this first couple of minutes that we have together, I hope that at the end of today, you will be able to estimate the technology readiness level of different technologies, or at least understand what people mean when they talk about technology readiness levels. And I hope that you will understand what types of risks we can consider when we are developing, when we are sitting in our lab, or when we're running experiments, we're planning our experiments, we're thinking about our projects, or we're even like on our undergraduate courses, and we are looking at, okay, this seems like something interesting, a new technology that someone is developing. What are the potential challenges that that technology might face in the future? You can think on that, about that as a consumer or as a researcher, as as in your daily lives, about the things you buy, the things that you hear about, the things that you hear about in the news. So it's really, really to think about, what does it take? It takes a lot of time, a lot of things to make innovations a reality. And the whole goal of the type of work that I do is, how do we overcome those risks? How do we look at these things early on so that we get ready for when they arrive? So exactly as I was saying, today the subtitle of this bigger 3 lectures is about risk analysis in sustainable bioproducts innovations. And we are going to go through today when we look at risks when we are developing what we call a technology plan. And as part of the technology plan, we have this thing called technology readiness levels, which we're gonna go through it together. And then I wanna to give you an example of, okay, we thought about this technology readiness levels. Now we have one idea of what they mean, and then we're going to understand what is early stage, so very early on the technology development, and why is it important that we look at risks, which is the subject of today's lectures, at the early stages. And then we're going to talk about what are those risks and how they appear, how they manifest, and then some take-home messages about these 2 parts. It's very simple, it's very basic, and hopefully in the question session, if you have any questions or anything you did not understand, feel free to ask. I chose to present today in English because it has been a while since I've given a lecture in Portuguese, but my first language is Portuguese, so you're gonna hear this kind of an interesting English mixed with Portuguese, at least a heavy accent that I have. But I just tried to make life easier for me. So, but I think that people from the event are organizing the translation, and but during the questions, if there is any term or anything that were not clear to you, I might be able to answer questions in Portuguese and English. So why are we talking about these risks in this technology development? I come from a background of forestry engineering, and chemical engineering. And in the sectors, in the agricultural, forest, even in the chemistry industry, they are going through a transformation, especially the forest sector. And they do their current business. They're there making pulp and paper, making packaging, making toilet paper, making various different things, which they're very good at. It's part of their current business, as you can see here. But then once things evolve, the world change, right? The bioeconomy term has been more and more used, and then there is a circular economy, and now we talk circular bioeconomy, and things can start getting complex. But over the years, to simplify these things, the sectors, the industries, the researchers, the whole ecosystem is thinking about how do we prepare, how do we plan, how do we transform? And every single sector transform over the years. We cannot keep doing the same thing the same way for more than 100 years. It's usually things transform, things change. And that's the whole idea of strategic planning. It's not about what you're doing right now. It is not very much about what we are doing tomorrow, but it's a lot about what we're going to do in the long term. How we are going to address new policy? How are we going to help fight climate change? How are we going to contribute to be on net zero, for instance? New policies that are coming on. How do we even measure the things that we do right now? How do we make new products? How do we make more profit? How do we enter new markets? How do we stay strong in the markets that we are already in? So this is all part of strategic planning. And through those strategic planning activities, these innovative bioeconomy business models are arriving. They really want to diversify the types of products that we make from bio-based resources. So I'm going to use some like generic words like lignocellulosics, or things that have cellulose, lignin, and hemicellulose, for instance, and which are components of plants. And I'm going to be talking about bioeconomy, which is the idea that the bio for me and for my lectures is the idea that we use plant-based resources or raw materials. And we create new things with these plant-based resources and raw materials, such as nanocellulose. And when we make these innovative bioeconomy models, they are usually built out of perhaps three things or two things in traditional business management studies, which is the technology plan, which from an engineering perspective, and the business plan, which is from a business perspective. And both of them are fed by the environmental analysis. Today, we are going to be focusing on the technology plan, and most of these lectures are about this part. This whole slide that you're seeing here, it's to cover it. It's basically a 5 credits course, which means 150 hours at least of work. So we are just doing, a little of a touch on some parts. In this case, is risk analysis, part of the technology plan. We are developing this new technology that will enable innovative bioeconomy models. So how do we do that? How do we do that in the lab? How do we do that in the companies we work for? How do we do that as being consumers that question things? How do we do that in our studies when we are in our undergraduates, our graduate programs, or working, or in our daily life? So what is a technology plan? And this is a heavy slide, but I just want to show you it. Basically, this would be the outline. This would be like the page that has a summary of the content of the technology plan. So we start with what is the technology we're proposing? Then we look, okay, is it feasible? Usually investors, this is the first thing they want to see, is if the technology is feasible. So we go through that. We think about comparing with others. We think about, IP is the intellectual property. IP stands for intellectual property. How do we make it? What are the processes? How does it look like? What is the inflow, outflow of raw materials, energy, mass and energy balances for the people from the chemical engineering side. And then we go to the feasibility analysis, or more development feasibility. It's not just if it all goes well, this is the economic potential. However, to get everything working, we need to make it feasible. And this is the risk analysis that we're going to talk about today. This is about, does this idea exist? Can we leverage existing knowledge? It is about what are the market requirements and risks. And then there is also the environmental perspectives. That is also a whole larger section. This is very, very summarized, and we are going to focus today just on this technology readiness levels and risk analysis. So let's dive right into it. About the technology readiness levels that you saw on the previous slide. What is it? And if we were live, or if we were in a classroom, I love asking this, especially when we have a diverse crowd of people, because not everybody uses it. And at first I was like, this is so obvious to me. Though, however, it depends on what path, what you're studying, and sometimes no one touches on that. However, this is very old, and it's used a lot in various areas, in research, in industry, by businesses. So what is this technology readiness level? Well, I have a very kind of ugly image here, but it's just to say that that's the traditional way of looking at it. It's kind of a thermometer. The thermometer as kind of level of risk. So early on, uncertainty. You don't know, you haven't proven yourself. As you go up, things get more of a cool, less risky or uncertain. What are we talking about? Early on, less mature. Higher up to around 9, more maturity. So it was developed by NASA. NASA was, they're amazing top secret projects. They were thinking on how they could send people to the space, and they have various projects, and each project were at kind of different levels. That they didn't know how to compare the projects to see which one was more advanced, less advanced. So they created this technology readiness level. Let's make it simple, so that they could compare their projects. But like not just NASA still uses it, but everybody else. And I'm bringing here the context of the European Union because now I'm working here in Europe, but before I worked in Canada, and before that I worked in Brazil. So it's used everywhere, and they all consider, especially from technology development perspective. So the low you are in the TRL, a lot of freedom of design. You can do lots of things. You can change things. Imagine you are in the lab. You can, mix and match, and it doesn't cost you a lot. It's not very much of a trouble to change things. But a lot of uncertainty. You don't really know the outcome until you test it. They've done little tests, so you don't know if really this thing is gonna work. But it doesn't cost a lot, so you can test. But then as you move up, as you move towards the TRL 9, 8, 7, the further up you go, you have less uncertainty because you have already tested things along the way. It costs a lot more, so you cannot change a lot of things. Imagine you have built a whole plant, and then you decided, okay, this process doesn't work, and now we have to change everything. So you need to build a new plant. Wow, millions and billions of reals, dollars, euros, whatever. So really, really something that you want to consider from early on all the way up. So the way of designing, creating new technologies is measured via TRL. Now let's kind of take one example of how important it is. So I think none of you know, but this is an image that I took from this program called Circular Bio-Based Joint Undertaking. If any one of you is interested in looking into how technologies are developed in the bio and circular economy in Europe, this is the most important funding mechanism. And how do they fund people, us, researchers, industry, anyone, businesses, anyone? It's via TRL. Each one of their funding actions or funding sources are packaged in little packages that are based on the TRL. So you see like these research innovation actions are from 4 to 3, from 3 to 5, And then 1 to 2 are other types of actions, more like base research, R&D. And then as you move towards scaling up, demonstration, then you are to 5 to 7. And then when you want to build the first biorefinery, what they call first of a kind, the first type of biorefinery, you are going more towards the 9. And then they have all these coordination actions that, for example, bringing people together. I'm bringing this example just to show you that is used by government as well. So it's not by, so far I've been talking about research industry, but also government. They also use that, and this is a European-wide. So even these projects to be funded, they have to involve various countries. And this is like a 3 billion euros or 2 billion euros joint undertaking. It's joint because it's industry and government, but it's I mean, the last one I think was 1 and now it's 3. I don't know, it's huge. That's the point. And he uses the technology readiness level, so it demonstrates the importance of that. Then I want us to now think about it. So we know that everybody uses it. We know that technology readiness level is used by government to fund projects. And then now us, researchers, how do we consider technology readiness levels? How can we think about this when we are in our work? Or how can we think about this as a student even? I'm an engineering student, and I want to apply this to this chemical or biological processes that I'm working on. So this is an adapted version that I developed from various sources, and especially from this very amazing professor, Sergio Beretta from University of British Columbia in Canada. So the way that he puts it as an engineer perspective is that we are very early on, so TRL 1 or 2. And in the 1, he has 0. So the idea is about the idea generation. It's about discovery. Then as we move along the way, okay, we can try to create a process integrated and see the steps. I do this, I do that, I do this other thing, and then I make a process at high level, at bench scale. So I'm using like a little beaker. I'm using like a small milliliter size reactor. I'm doing it in the lab, and this is a bench scale. So this is TRL 2, very high level, but however, I have thought about the process and how it integrates. Now we want to see if it's feasible. And from an engineer's perspective, a lot of the time, feasibility is about techno-economics, TEA, techno-economic analysis. And then I do this techno-economic analysis, which means, can I achieve all the technical perspectives? Can I get the right strength, wetness, I don't know, hydrophobicity, right? Which doesn't like the water. Or can I make it flexible? Or is it rigid? Is it fluffy? Is it, I don't know, is it strong? Is it soft? Whatever technical perspective I need. Then economics is more about energy intensity. Is it way too expensive? Can I even, do I have any type of reactor that can deal with that? Is that, could the potential cost in the future compete with the existing potential applications? To be able to do a techno-economics analysis, we need to know what is the end use. Even though sometimes we prefer to leave it open. Oh, this is a platform technology. It can be used for, I don't know, in the concrete industry, it can be used in the agricultural industry, it can be used in the chemicals industry, it can be used to make, I don't know, foams, to make wallpaper, to make whatever, bioplastics, many types of things. Though that means that there's a lot of uncertainty. I don't know, how can I analyze the feasibility if I don't know yet what the best use for? Because each one of these applications have different technical requirements, different market prices. So how can I do this? So in this idea, we start narrowing down to see the feasibility. And it means that is a feedback loop. We go back. And then when we go to the 4, can we make it now that I looked at the feasibility, that I think about this is the best application, can I now go back to the lab and make it a little bit bigger? Try to make it in an integrated way. This is about pre-pilot. This is about even having, like, imagine a miniature of what the process would look like in reality. That is about development. Now, when we make things continue, I see, oh my God, I cannot recover the solvent use. Oh my God, I cannot really grind my fiber well enough that the way I was doing in the small grinder that I use in the bench scale. Now I'm making things bigger. Oh, now I realize that I actually have a lot of impurities that I didn't have before. Or now that I made it into a continuous process, the yield decreased. I'm making less of this chemical that I need. So, and that makes it infeasible. So we go back to the lab. And as we go through that, we think about such as technology readiness level 5, which is the last one you see there, is about I want to make enough volume, enough of a prototype, so that I can de-risk the technical aspects of the technology, make the performance work, and make enough of the product that I can give to a potential consumer to use it and test, that I can make prototypes. And when we implement it, then we translate the full thing into that big package. Remember at the beginning of this lecture that we talked about, right, the disruptive innovative business models, and then we had the technology and the business one. So when we put an environmental, when we put this together, we developed this engineering plant design. So there is a back end, the front end engineering. So if we have our engineers here, you might have seen that before, and you might have had a full year of a course that involves that. So it's really about the plant design. How do I build a commercial scale plant? Then this is the plan. Usually we go into phases, so we don't just build right away. We would build a demonstration plan first. Then we would commission the demonstration, and then we would scale it up to deploying it at commercial scale. That's the first commercial. It starts at TRL 8. And then, you know, with TRL 9, we are finally making enough product and selling the product to the market. We have penetrated the market. We have customers. We are running the mill. Things are working. We have already a product being used. We can even think about that the product is being in the market and we consumers are already buying it. So it's really about getting the technology up and running and commercialized. So this is an engineer's perspective. You can see it's focused on the technical and economic, especially perspectives of developing this chemical and chemical biological innovations. Then, okay, oh, this is a lot of theory and this is kind of boring. So how can we think of an example? And I see I am from Rio Grande do Sul, so this is something that in Brazil you might have seen, you might have not, but this is basically my fuel, so that I can keep, you know, excited. But this topic does excite me as well while I'm talking to you. So let's take a look at some examples while I drink my chimarrão. This is a very interesting technology, but that has not yet been proven to work commercially. And I took this figure from my dear colleague, Michael Hummel, which is the mastermind behind bio-based carbon fibers. And this is basically just to show you how we can show technology readiness level from one technology platform. This is his technology, his process, his patents, his work from his research group of 30 people that have looked at, of course, they have worked with textiles a lot. This is just like one of his research areas. But they had an idea, first concept. Then they tested the basic principles. Then they, okay, let's apply this. Let's try in the labs. Let's run several different applications. And at the same time, we are looking into who are the partners we can work with when we're thinking about applications, to be able to think about the partners. What does it take to scale up? So then he got this grant at Technology Readiness Level 3 that he could prove the concept. So they actually built, they are between TRL 3 and 4, but they do have a continuous line of production of carbon fiber. And they went all the way to Australia to test it in a larger scale carbon fiber manufacturer. And then they troubleshoot, and then they saw what doesn't work in their process. They went back to the lab, they ran it again. Then they came up with the right process parameters for carbon fiber production. That in that case, and they've also realized that using an exact existing, the same type of carbon fiber manufacturing process that uses PAN, polyacrylate, something like that, to make carbon fiber did not work for the carbon fiber from lignin cellulose or a mix of lignin and cellulose. So wood-based carbon fiber. Then they went back to the lab, they built their own pilot, pre-pilot, perhaps large lab scale, what they call. And then they made this replica or a mini size of a full production line of carbon fiber, and now they are applying and they have optimizing the process. So now they are looking at the feasibility around here of that process, troubleshooting, before they actually go further with the existing collaborations and go into more funding to actually build a prototyping. So basically building here the CSS system lab, but this is about a pre-pilot pilot, and 6 is about a demo, and 7 is a demonstration to actually getting into a final commercial application. Now I want to bring an example from a paper that I found just preparing for this lecture that talks about nanotechnology enabled plants agriculture. So this whole paper, which you can find in Nature Food, and here is the link, it's quite interesting. It looks at the various, so you have seen here, I'm sorry, it's a quite busy slide. You have seen here in this graph the various different types of applications of nanotechnology in agriculture. And in the bottom here, you can see the technology readiness levels. And this is exactly the same graph that I took exactly from there. It's their graph. This is the explanation of the graph. So, and then here, they even looked at the performance level, technology performance level. So what would really that technology be targeting? Would that be really heavily changing or replacing something that exists, or improving something that exists, or completely changing something that can have like a large amount of disruptive impact as you go up this axis. So you can see in research, there are different levels. And one of my key points here is that you need to think about the application. So this is about nutrients. This is about the growth enhancer. I actually work for a startup that was developing nanocellulose growth enhancers. This is about coating seeds. So this is about the end use of the nano. So this is about early stage proof of concept. This is about, so this, I would call it ideation, lab testing. This is actually going into and making the product and testing it at the end of the as the end use. And these few trials is like large scale trials. Validation and commercialization is like, okay, we are actually working with end users, and we might be able to even start selling some of those applications. So here you can kind of have an idea. So for pesticides, we are very advanced. Those nutrients, nanoactives, we are quite advanced. Here, I guess, nanosensors, micronutrients, growth enhancer, we are still at early stage trials. So this gives you an idea on how this is a very interesting graph, how there's different applications of nanotechnology enabled plant agriculture solutions are their state of the art. And this was not that old, so 2020. Things have not changed a lot since 2020 because of the pandemic and everything else. But this is a nice idea of how we can even look at technology at early stage, that technology readiness level can help you understand where they are, how they compete, and how they are growing, and what can be their impact. Now, let's close this in this first 30 minutes. I want to close the part about TRL, this introduction and TRL, and then we're going to deep dive into risks, and then close around in the next 20 minutes. What is important about TRL? It helps us identify what is the work ahead. If you're very early, we have a lot of work and development to do. If you're later on the TRL, we have less work to do, however, we have less freedom of design. It helps us assess risks, so that's why I'm presenting this part first before we look at risks. The early on, more risks, more uncertainty, but more freedom. The later on, in theory, we have the risk, the technology, as we build a demo, a pilot and a demo. And if you ask someone about TRL, keep that in mind. Every people have a different view of TRLs. I presented the engineer's perspective here today for you. You can consider that, or you can even read and get your own. It's depending on, you know, how advanced you are in your studies. You start building your own perspectives about TRL. And if you ask a CEO, a chief executive officer, they will say, this TRL is very low because they're trying to invest. They lower the TRL, in theory, more risks. I can decide to invest less because I am taking a lot of risks in return. And then if you ask the owner of the startup that is pitching that, or even the researcher that is pitching their patented process to someone, they can say, no, this is TRL 5, but actually the CEO might say it's TRL 3. So it depends on the person. It depends on where the person is positioned to see where the TRL is. So just to say that there is nothing set on stone, that it varies a lot. But why are we looking at this TRL? Why are we looking at risks at early stage? This is kind of my pitch of today, and what I want you to keep in mind. Early stage is TRL 1 to 5. Not further than 5. So it's before I actually build something that is of demonstration scale or even pilot scale. We are still on the pre-pilot, maybe TRL 4, early stage risk assessment. Why? And I have a quick story to tell you. This figure here is of it doesn't have much to do with like nanotechnologies. This is a pulping technology, and you might think everybody makes pulp, wood pulp, agricultural pulp in Asia, with straw, with bamboo, with various things. But this was something that was new to some extent, done in the US. It was called Columbia Pulp, and they had this whole infrastructure built. It was a lot of marketing about the first straw, tree-free, so no tree coming into the mill, only straw pulp, only straw was being used, wheat straw was being used for this pulp mill. Then I was looking at this and I was preparing for another presentation last week. And then I thought I'm gonna check how they're doing, because I looked into this project in 2018-19 when they were building the plant. And then just to give you some background, right? So wheat straw, wet lab, pulp, whatever, there's some technical information here. Just all to say that this is TRL 9. It was the first in North America. And a large scale, in theory, the process, we were talking a lot about technology and process. The process was looking quite nice. The marketing of the technology provider was very good, and actually they have licensed it. So people were paying them to use their technology in various, at least 4 different places at that time, by 4 different projects. And then I was, okay, it's time for an update. Because at the time we were like, wow, this is huge. They're building something big. So they must have gone through all the risking. And then we interviewed the CEO, we interviewed the technology provider, we talked to experts at the time. And we saw, one thing we saw was like, they seem to have jumped the pilot and the demonstration steps. They really rushed into building the large plant because they saw an opportunity market-wise. There was this whole trend of not using trees, using residues. In this case, it's residues from agricultural sources. And the main thing we saw was that they didn't have a lot of pilot and demonstration data, so they were scaling up a small, like a lab scale process, especially for, so they are making pulp, and then the rest of it is this soup, this big mix of biopolymers. The lignin, the hemicellulose, and the spent chemicals would all be in the soup, and then that was going to be sold as a product for, you know, dust control, animal feed, de-icing, pesticide, and fertilizer. So in the agricultural as well, because we're thinking we are in the middle of this agricultural region, so we're gonna sell to the farmers the soup that can be a soil enhancer, can give some nutrients. And we don't want to do anything with this. We're not going to transform, we're not going to make it into products. We are going to just sell as is. And they only had this huge storage tank that they would keep this biopolymer and sell it. So which means that if no one buys this biopolymer, they have to stop producing pulp, because they will produce more pulp, they will produce more of this biopolymer soup mix, whatever. So they had to ensure that they sold that first to be able to even make the pulp, which was the lowest risk technology-wise product of their portfolio. And we were really worried about that, because if they make too much of this and they don't sell it, they don't even have a waste treatment plant built. They just have this big storage tank. So that we were even worried, like, how did they get environmental permits to build it? But anyways, I don't know. Then I checked back on them and things went really wrong. They closed the mill. They was auctioned. So they were owing money to lots of people. And they had to close the mill, fire everybody. And the only thing I was able to find about it was, of course, like official local news and the municipality and the state news about the auction. And this is like a print screen figure from the Times, like the local journal, that said in their article that they had market development challenges and production challenges. And remember the risks we saw when they were building the mill, and there was a lot of optimism, was that they did not did the demo, they did not do the pilot, that they didn't deal with how these products will enter the market. Like, can we really use them right away the way they are? Do they need any modification? Especially, we're putting something into the soil to make food. So there are lots of regulations about that as well. There would be some challenges in the market development, product development as well. This is to say we cannot skip these two parts, and we need to look at the risks, because these are all risks that were identified. So even though the technology readiness level of their pulp making process was very high, the technology readiness level of their biopolymer waste stream for these end products was none, or was very low. So was it the idea, or early stage development? The whole point is that we need to consider these risks, and this is a bit of a big sentence or phrase here, that if we look at this risk at early stage, we can actually guide research and development and improve this feedback loop and see what do we learn from making this pre-pilot thing. What is lacking? With lacking this feedback can make this whole first of a kind commercial, what we saw with Columbia Pulp, to be a huge fiasco, or even a huge sad story, right? Because imagine all those people, that was at least, I think it was 90 or 70 or 90 people working in the mill that were fired. So, I mean, we want to prevent those things from happening. So, but then what risks, and how do we look at risks? So the next, per se, 15 minutes, we are going to talk about risk categories and some examples of risks. Here is just a laundry list for you. So risks can be related to technology. So how is the yield? Can we scale this? Are there any hazardous things coming out of this process? It can be related to market. Is someone willing to buy this thing? How is the market going? Is the market seasonal? It can be related to product. What am I making? Is it one thing, two things? What's the portfolio? What is the ratio between the types of products? Is it a commodity? Is it a specialty? So what are the regulations related to the product? And what do we do with the product at the end of this life? What is the footprint? There is a footprint of the process itself. the footprint of the whole value chain around the product that you are making, from feedstock all the way to making the product, all the way to selling to the consumers, all the way to dealing with the end of the life management. And then from a business perspective, remember, they weren't market ready. They need to understand where you enter the value chain. You need to understand, is this potentially circular, or is it a linear value chain? And then, of course, where is the feedstock coming from? Is it secure? How expensive it is to even the feedstock or the end product? And maybe making very close to the feedstock, but I need to ship my end product all the way to the other side of Earth, I don't know, other side of the world. That can be very expensive, especially when we are making large commodity products, such as pulp, or when we are making specialty products, such as fine chemicals, or I don't know, a special growth enhancer for some type of crops. Then it's a special product, which it might be okay to ship further away. Because there is margin in the selling price. And then who do I collaborate with? And then what were the competitors around? Are there any conflicts of interest if I'm making this product with another partner and then we are both trying to reach the same markets, for instance? So this is all types of risks. There are many more. And what I want to bring it to you, and we don't have the time to go through all of them. I have 15 here. You're going to see they're heavy slides, though. Let me charge my laptop, which I don't have the charger here. But I think we can probably continue until the battery. Yeah, we have enough battery. So what are the unsolvable constraints or bottlenecks in the process? So I put a little star there because I'm going to exemplify this one. I'm going to give you 2 examples, but for the 15, I'm going to quickly just demonstrate to you that you can stop the video, pause, and then you can take a look at each one of these, okay? Because we don't have time to go through each one of them, but I want you to have them home so that when you want to go back and you want to have this database of risks, you can look at them. And then number one, I'm gonna to give you an example, and one more, 2 examples. So there are things in the process that we cannot resolve, such as I don't know, that we can never scale up the reactor needed for that process, or there is in some way the conversion cannot be reached to an yield that is required to make it feasible. We are making some type of VOCs or some type of exhaust pollutants, or we cannot separate the product well enough for the desired needs of the market. Then as we go to another list of risks is about we're using operations conditions. We're using too much energy or very high pressure. Do we have freedom to operate? Is someone else already owns this technology? Raw materials and feedstock. So can we get long-term supply, for instance? Is the supply at risk? We can lose to some extent the efficiency of catalysts, and we cannot recover solvents. These are some types of risks. And the another one with the star here is the market potential. So I'm going to go through a little example with you. But in this case, we really want to think about the size of the market versus what we want to produce and in which scale. And then product portfolio margin, can we really make it a good economics? Can we make internal rate of return that is attractive? Does it cost a lot for the end user to switch their manufacturing process to use the proposed product? Is it required? Can they take the product as is, or do they need to change their own process? How diversified is the type of product that I'm making through that technology? What are the different end markets? Each one has specific needs and characteristics. And then the last three risks that I want to exemplify, and that there is a list of 150 plus, but I just brought some that usually come up on early stage development. By early stage, I mean we are still within lab, but we should be thinking about these things. What are the regulations, the standards that this type of technology and product need to overcome? Regulatory issues, get the approvals. And these are any problems with handling the product at the end of this day, to ensure that we can transport it, we can deliver it, and it's going to maintain its quality. So big laundry list, you can pause the video, look at the explanations. I gave a very quick overview. And then I'm just going to give you two examples. So we talk about technology, bottlenecks and constraints. This is about the full process. And I just have one example for you. This is about how much development work is necessary to make this a full process, and what is the technology readiness level of each part of the process, and what is the risk to taking that into commercialization, to taking that from TRL 1, 2, 3, all the way to 9, all the way to successful commercial. Here I have one interesting fact that I worked for this project, and this is an image just for exemplification. I'm not talking about this necessarily project, but you know that nanocellulose is made into commercial or even commercial scale nowadays. You can buy it. So it's at high TRL making nanocellulose. So in theory, the technology is very well de-risked. But then in some processes, the nanocellulose comes into a wet form, and we cannot transport. It's too expensive. I mean, sometimes it's 90% water. So imagine transporting water around, and even the end user prefers it to be semi-dried. But then when we look at how do we dry it, then there is no technology that has been used specifically for that application. There are tons of drying technologies, but dyeing technologies for nanocellulose are at a very low TRL, and I know this from experience. So it takes many years, and I have seen that at least 3 years, 4 years, 5 years, just to take existing technologies, tweak it, design it, improve it, or design a unique technology that will dry nanocellulose and maintain its technical specifications and achieve the drying requirement for the different end applications. So I just want to emphasize that it does take time. The other example I have for you is technical. Now is market. Technical perspectives are taken into consideration when we're developing the process, when they're thinking about the application, but then the market potential is also something to be looked at very early stage. Is it, how much should we be producing? How big would that plant be? Does the market really needs that? Is the intended, imagine if we're making, I don't know, because pulp is a huge manufacturing power, right? We make a lot of pulp. Imagine if we now take all the pulp and we turn into I don't know, we turn into carbon fiber. We take and make cellulose, and we make cellulose into carbon fiber. But the carbon fibers are a small market. So we wouldn't never need a lot of pulp to make into a yarn, to make into mix with lignin and make carbon fiber. Then, you know, we would be disrupting this market in a way that it's not even perhaps beneficial to our strategy. So we need to look at how much is being made, for what applications, what is the niche potential of this technology. And that's how we would design back the technology itself. I'm using carbon fiber because this is a project that I ran recently. And so there is more production nowadays than demand. However, the demand is expected to grow significantly, so more than double. But if you look at the size, it's very small. The largest carbon fiber manufacturing plant that I've read about is about 200,000 tons per year. And that you use 1 kilogram of carbon fiber needs 2 kilograms of pen. So basically, the pen plant is larger than the carbon fiber manufacturing plant. So if we want to make this from bio-based resources, then how big should the plant be? Because we already have capacities of lignin if we want to make out of lignin only. We have lignin extraction plants of 50,000 tons per year. And the largest CF manufacturing plant is 20. So we could use it entirely to make a very large carbon production plant out of lignin, for instance. Then we should also look at what is driving this production. For instance, in this case, there are various applications. Which is the application? Which application is growing? Can I use my bio-based carbon fiber for this application? And how big should this manufacturing site be compared to the existing carbon fiber production facilities nowadays? And then we also should be thinking about if we need 1 kilo to make 1 kilo of carbon fiber from pen, we need 2 kilos of pen. If we're making from lignin or a mix of lignin and cellulose or just cellulose, then how much would that ratio be, to think about what the capacity should be. Then we need to think about exactly what I was saying. What the capacity, what is this the capacity impacts the existing market for that end application you decided to go for? How do we use the existing cellulosic feedstocks, so lignin or cellulose, and how big should it be? What does the market needs? And I mentioned in the previous slide is that cellulosic production is huge. Lignin production is smaller, so perhaps we can make carbon fiber from mixing both, but the capacity would still be very small compared to the capacity of an open paper plant. And then how much lignin and cellulose you would require to actually make 1 ton of bio-based carbon fiber as well. So these are all things that need to be answered and need to be considered even at very early on when you're designing what is the capacity of your pre-pilot or your very small capacity plant. I'm almost closing this presentation. These are the takeaways. So risks change. So when we are early on in the development of a technology, there is one set of risks. As we move further in the technology development, the risks change. There is the need for a constant review. Remember our feedback loop that I showed you? That applies to TRL, that applies to risk analysis. The risk analysis informs the technology and the business plan. So it's not just about the technology, as I mentioned before. It's also about the business strategy in the future. And if we want to take things out of the lab into commercialization, and that they can be very general and they can be very specific to the technology we are working on. So these are the take-home messages. It was a lot of information per 50 minutes. I just want to really thank you, and thank you the organizers. Have a great day and see you tomorrow. Bye.